Okay, let's get back into this Kruskal-Katona theorem thing. So just remind you of the Colex order. If I've got two sets, with size k, where their elements are like A1 up to AK in increasing order and B1 up to BK. A is less than B in Colex. If AI is less than BI, where I is the max index, where they differ. Yeah, probably everyone knows. I've heard a lot of people talking about the assignment. So yeah, there's assignments due tonight, unless you, in case you didn't remember that. Yeah, last time we kind of gave a formula. Like if I give you a set A and I say which position is it in Colex, we gave a sort of expression for how many things come before it, which tells you where its position is, right? So it's useful also to understand, like, well, remember Kruskal-Katona is trying to say, to minimize the shadow, I should take the first sets in Colex. So if I have a collection of size m, to minimize the shadow, I should take the first things in Colex. It's kind of useful to know how big is the shadow of the first things in Colex. Like that tells us what we're trying to aim for as a lower bound. So for k at least 1 and m at least 1, the size of the shadow of the first m sets in Colex order on the naturals choose k. So this is kind of a, if it's not clear what this means, let me know, but I'm just saying, like, yeah, just writing this in words. So the size of that shadow is the sum I equals 1 to k. So I'll explain what AI is in a second, but AI minus 1, choose I minus 1, where A1, like, where, so this is an increasing sequence of numbers, A2, A1, A2, etc., such that m is equal to 1 plus the sum I equals 1 to k, AI minus 1, choose I. It's kind of a weird way of writing this, but right. But you could, kind of contest and say, like, how do we know that this sequence exists and how do we know it's unique? But we actually proved that. That was like a corollary of one of the things we proved last time. So like for any m, there is a unique sequence where m is equal to 1 plus this sum. There's a unique increasing sequence with that property. So if you take that sequence, and I say, how big is the shadow of the first m sets in Colex, you get this very similar sum, except it's like choose I minus 1 instead of choose I. Okay, so the proof of this actually pretty much goes by the same argument for one of the things we did last time. You just say, okay, well, I mean, maybe I'll just sketch the proof and not give all the details, because this one it's not really hard to work out the details once you know what you're doing. So proof, kind of sketch. So, well, the set, let's say A, which is like A1 up to AK, that is the mth set in Colex by the lemma we proved last time. Then you just say, okay, well, what are the sets that are in the shadow of, like, well, the set A and all the things that come before A. So for example, the shadow of the first M sets in Colex, for example, contains like all of, if I take sets, so all the sets of size M whose largest element is less than AK are in the first M sets because they all come before A. If I take one of those sets and I remove an element, I get a set of size K minus 1 whose biggest element is less than AK. So like these are in the shadow of the first M sets because, and then you've also got things like, oh, it could have the point, it could include AK, but then the next largest element could be less than AK minus 1, and so on and so forth. So this gives you like the last term of this sum. And then you look at, the sets that contain AK, but whose next largest element is less than A sub K minus 1, and so on and so forth, and you just add it up. Well, maybe I'll just do one kind of more step. So it also contains all sets of the form, let's say S union AK, where S is in A sub K minus 1 minus 1. Choose K minus 2. And then I'll just say and so on. One useful thing about this lemma is it gives us a way of writing a more explicit statement of the Kruskal-Katona theorem. So last time we said, basically we expressed it as like the shadow is at least as large as the shadow of the first M sets in Colex, but that doesn't really, that's not a number. I mean, it is a number, but it's kind of, you have to compute it, right? But now we've kind of computed it in that lemma. So I'll just say this is the same as the Kruskal-Katona theorem. So this is Kruskal-Katona kind of restated. So for K at least 1 and M at least 1, take this sequence A1 up to AK, this increasing sequence. such that m equals 1 plus the sum I equals 1 to k, ai minus 1 choose I. Okay. Which, yeah, exists and is unique. So if f is in n choose k, naturals choose k, and the size of f is m, then the conclusion is that the shadow of f has cardinality at least the sum I equals 1 to k, ai minus 1, choose I minus 1. So last time when we wrote the Kruskal-Katona theorem, we said the shadow is at least the size of the shadow of the first m sets in colex. But we know what that is. It's just that number in the lemma. So we can just write the number, right? Any questions about that? It's still a little bit implicit because it's like to figure out what's going on, you have to find this sequence. But anyway. So for any m, you got to first find the sequence, and then you can write the bound. Okay. So here's the basic strategy for proving this. Take a collection. Take an f in naturals choose k. And suppose I can transform that collection. Okay, of course, if f is the first m sets in colex, we're done, because the bound holds. So if it's not, what I want to do is kind of shift. So take elements of f, which are kind of late in colex, and replace them by elements that come earlier in colex. And if I can do that in a way that doesn't change the size of f, and also decreases the size of the shadow, I could kind of keep doing that. So I find another element, replace it with something earlier in colex, make the shadow even smaller, or say the same. If I can keep pushing things earlier in colex and keep shrinking the shadow, then kind of when I'm done, yeah, we should, that's sort of a kind of strategy. So here's one way you can shrink things in colex. Well, if I've got a set in colex and I take an element from it and pluck it out and replace it by a smaller element, well, that's one way to decrease it in colex, right? Basically, colex order, the earliest sets are the ones with the smallest elements, right? So here's an operation for doing that. It's something called a compression. So let's say for I less than j, define Cij to be a function from the power set of the naturals to the power set of the naturals. And it's defined in the way that I kind of said. I mean, basically you want to, for any set, I want to kind of try to take out j, the number j, which is a large number, right? J is bigger than I, and I want to replace it with I. Obviously, like if it doesn't have j, then I can't do that. Or if it already has I, then I can't do that. But if it has j and it doesn't have I, I'll just pluck out j and put in I instead. So I define this by Cij of a set A is equal to A, take away J, union I, if J is in A and I isn't. And otherwise, I just map A to itself. I just don't change it. And like a kind of key observation here is that if I apply Cij to some set, it's always going to come, well, maybe I'll put an equal sign because it could be the same set, right? So either it's going to be the same, it's just going to be equal to A, or it's going to come earlier in Collex, right? Because basically I've just replaced this big element with a small one. Is that clear? Okay. So I kind of, essentially what I want to do is I take a collection, I want to apply this, oh, and by the way, this is so Cij is called the Ij compression of A. Yeah, it's kind of a compression because you're kind of compressing things towards the beginning of the natural numbers. So essentially what I want to do, I take my family, and for everything in the family, I want to try to compress it. It's a little bit dangerous, though, because you may end up turning two different sets into the same set when you compress them, right? If I have the set, like my Cij, or let's say C 2, 5 of 1, 3, 5, 6 gives me 1. So it takes out 5 and puts in a 2. So it's 1, 2, 3, 6. But C1, 5 of 1, 3, 2, 3, 6, like the same set I ended with, is just itself, right? So if I had a family that already has 1, 2, 3, 6, and it has this thing, if I just try to compress things, I'm going to get the same set twice. You don't want to do that. That'll change the size of the family. So we have to be a little careful. So here's how I'm going to define the compression of a family. So for a family of sets of naturals, the Ij compression of F is, so I write it as Cij F. So first I'm going to apply the compression operation to everything in my family. Okay. But because this compression is not a bijection, it's not injective, so this might actually have fewer elements than F, because again, two things could map to the same thing. So I'm going to kind of fix that by adding in all A such that A is in F and Cij of A is in F. yeah, notationally, it's kind of hard to like parse what's going on there, but yeah, this turns out to be the right definition. So the property I want this to have is what we really want is that, first of all, we don't want this operation to change the size of the family, because that would just be weird. I don't know what we would do with that. So like we want this operation to keep f the same size. But we also want the shadow to not get bigger, because if we keep compressing and the shadow keeps getting, at most as big as it was before, and we end up at the first m sets in colex, then and at every step the shadow gets smaller, then definitely that's a lower bound on the size of the shadow. So we want that. So secondly, we want the shadow of this thing to be at most the size of the shadow of f. Does that make sense? Yeah.
So we've kind of dealt. That get dealt with here?
I don't think so. So yeah. Let's draw. So I'm going to prove this, and we'll kind of draw a picture, and maybe it'll be clear why that's not possible. But yeah, essentially, yeah. So the question is, could you have two different things kind of get compressed into the same thing? I mean, in some sense, the answer is yes, but only if one of those things, the compression was kind of trivial, and it just gave you the setback. Because yeah, if you think about it, I mean, well, actually, when the compression does like a non-trivial thing, it takes out j and puts in I. Now you can that's kind of reversible. I could put in I and take out, or put in j and take out I again. If you had two sets that like did a non-trivial thing, they would have had to be the same to begin with. Like basically, yeah, if they ended up in the same place, they would have had to be the same, because you could just reverse this, take out I and put in j, and yeah, they would have been the same to begin with. Yeah, let's prove that the compression doesn't change the size of the family. Well, maybe proof is a strong word. Let's kind of just draw a picture. So this is kind of below the standards that I expect in the assignments, but yeah, I guess I'm not getting marked, so I'm allowed to do these kind of things. Yeah, so here's a picture. So if I think of all of 2 to the, okay, I don't really know how to think about if it was, let's not think about like crazy things like uncountability. Like these are finite sets. So 4 finite f. This is combinatorics, right? Because like technically these things could have like infinite, they could be uncountable, countable, whatever. I don't care about that. We're just doing finite sets here, right? So if I look at the power set of the naturals, I can kind of break it into 4 kind of things. So sets that have j, so with j as an element and not I. you've got sets with I and not j. You've got sets with both of them. So when I say with, I mean as an element, right? So these are sets that have I as an element and don't have j as an element. You've got sets with both of them and sets with neither. So without I or j. And so now I'm going to kind of draw what the compression does to these sets. For most of these collections of sets, the compression doesn't do anything, right? Like if a set doesn't have I and doesn't have j, the compression just does the, it's just the identity map. If you've got both I and j, it's also the identity map, right? So these arrows are like trying to say, like, kind of the arrows in between here are describing what does Cij do to the sets. Also, a set with I that doesn't have j, that's also the identity. So if you look at it, I guess this, yeah. The only the only types of sets that it does like a non-trivial operation to are the ones that have j, so with j and without I, right? And it just switches j and I. So here, so each set that has j and doesn't have I gets mapped to a set that has I and doesn't have j, right? It just switches them. Is it clear what I'm depicting here? Okay. We haven't talked about F, right? So this is just looking at what it does on the entire power set. So let's think about F. So any sets of F, so I'm going to kind of draw some dark blobs here. And let's say the dark blobs are sets in F, right? So F contains these ones, and these just map straight across. So like, and same, It's like these classes where we have to think there's something interesting going on, right? So here, if I draw blob, 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 these just get mapped straight across. Things that are up here, so this point, if the place where it maps to doesn't already have like one of these sets is not already kind of taking that position, we kind of map that to here. So when I define the compression of F, so any of these sets here where the compression of it isn't already in F, we kind of count it over there. That point ends up in the compression of F. But for something like this, where the corresponding set is already there, like this is where we would have non-injectivity. Like two sets would map to the same thing. And therefore, to keep the thing the same size, we also keep this set. So So I'm claiming that this proves that these things have the same size, right? So we either take the compression, for every set in F, we either take the compression, well, we always take the compression of it, but two sets may have the same compression, but that only happens when one of them is from here and one of them is from here. That's the only time that they could have the same compression. And that corresponds to a set in F whose compression is already in F. And kind of those ones we add in this second part of the union. Yeah, maybe this proof by, I'm not sure if this proof by picture is clear enough. If you did an example, you'll start to see why it works. Okay, so let's take this as a given then. So the more complicated thing to do now is to show that the shadow can't increase. Maybe I kind of want this this board here, the definition. So I want to show the shadow can't get bigger when you compress. This one's going to be a horrible case analysis. Probably like 6 cases or something like that. We'll see. Well, maybe we call them kind of 3 cases, maybe with 2 sub-cases each, so it's kind of 6 cases in some sense. Yeah, I apologize in advance. Let's get into but let's just do it, and then we just know it's true, and then we don't have to think about it anymore. Yeah. This course, I like to just do things that are beautiful. I don't really like proving the Kruskal-Katona theorem. Now I'm saying this in public on YouTube, but it is such a powerful theorem. We have to do it basically. Okay, let's prove this. So this is here's a clever thing about this proof. What we're going to prove. So we're going to prove this, but we're going to prove it in an interesting way. So we're going to prove that if I take the shadow of the compression of F, that this is a subset of the compression of the shadow of F. So remember, F consists of sets of size k. I haven't been rewriting that hypothesis, but this is sets of size k. The shadow is sets of size k minus 1. But it's clear how the compression, well, actually maybe we defined it in general anyway, so yeah. But a reasonable question at this point is, why is this like good enough? Like, why is this relevant? And well, the reason is, what if I take the, take the cardinality of both sides. So I'm going to call this statement star. And what we're actually going to prove is star. If I take the cardinality of both sides, so then that'll be at most that But can anyone see why that's like a good thing? Why that's good enough? So we actually want this, but we've got this.